Okay, have a good day, students. So let me give you an introduction about the quantum physics. So this is just an introductory class on quantum physics. So you might have heard about this quantum or quanta. So these things you have already heard. The quanta of energy. These things you might have heard. So what is quantum physics? This quantum physics originated because of the failure of classical physics. Okay, so first of all, we should know what is classical physics and what is quantum physics. So, what is classical physics? This is the physics we are using from olden days. So, whatever you are seeing through a naked eye, or it explains about the macroscopic world. It explains about the macroscopic world. So whatever you are seeing, there is a ball, movement of a ball, okay, or a car, or any other vehicle, train, whatever it be. So where it is moving, okay. So these things, if you study the motion of these things, so this is possible, okay, and you can find if you have a projectile motion of this ball in a particular angle, you know where it ends. Okay, so the projectile motion. Using the Newton's law of motion, you can easily find that at which distance, at what distance it will uh, travel. So these things, even you can use this equation to find the value of the velocity of the ball. Okay, so a bowler who is bowling to a cricket batsman. So immediately after that ball, they will mention that the ball is about 150 kilometer per hour. Okay, or 145 kilometer per hour. So these things are possible with the help of these equations and all. So in the macroscopic world, it is possible, and you know that this ball or this any material which having a certain mass, so it will move in this direction. So it will attain this distance. So these things you can easily understand. Okay, and practically also it will give the same result. But in the microscopic world, in the tiny world, so where the human can't see that, particularly in the atomic dimension. So particularly inside the atom, you have the proton, neutron, that is inside the nucleus, and it is surrounded by the electron. So these are the subatomic particles. The behavior of this movement of this electron, proton, you couldn't predict that electron movement. Okay, so the behavior of the particle is different when compared to the particle in the macroscopic world. Okay, so the classical physics failed to explain some of the things I'll tell you what are the failures of classical physics. So it failed to explain the black body radiation. Failed to explain the black body radiation. And in addition to that, photoelectric effect. So for which Einstein got the Nobel Prize, photoelectric effect. And the last one is Compton effect. Compton effect. Okay, so black body radiation. What is the black body radiation? So you might have heard about this black body. So black body means it's a body which is absorbing all the radiation at first, absorb all the radiation. Okay, it absorb all radiation and re-emit all the radiation. So what is happening here is, so with this black body, Planck, so he has given a theory with his own assumption. So Planck's theory, so his assumptions are, so by absorbing this radiation, okay, so this radiations are absorbed by the atoms. Atoms absorb radiation in black body. Okay, so in a black body, the atoms present in the black body they absorb the radiation. Okay, and what happens? While after absorbing the radiation, so it is in the form of energy. So it start to vibrate. Atoms start to vibrate. Atoms start to vibrate. So different atoms um, absorb different kind of different energy of radiation. So it vibrate in different frequency, different frequency. So what happened? So while doing the vibration, it start to emit the radiation. Whatever it absorbs, it is emitted by the atoms. Okay. So that has happened here. Since it is vibrating, this is called as atomic oscillators. Atomic oscillators. Okay, so this is an important term. So first it absorb all the radiation and it start to vibrate in different frequency. Different atoms vibrate in different frequency, and they are called as atomic oscillators. Okay. So the frequency of the vibration, so that is equal to the frequency of the radiation emitted. So this is the fourth assumption made by him. And then, um, as per the classical physics, they said that the energy emitted is continuous. But according to Planck's, the energy emitted is discrete. The energy emission is not continuous; they are discrete. Discrete means you have studied about the discrete. I think you may study in the future discrete mathematics and all. So discrete means it is happen band by band manner, um, not in a continuous manner. So according to classical physics, it is mentioned that it is there is a continuous flow of energy from the black body, but uh, he said that there is Max Planck said that the energy emission is in discrete form. Okay, here next we can see. So that is atoms are vibrating. So different atoms have different frequencies and all, and the multiple of small quantities of energy. So they are called as quantas. So they emit the radiation in the form of multiple of small units or small quantities of energy. So they are called as quantas. So as you know, that is a packet of energy. So packet of some radiation. Okay. So from this assumption, you can say that multiple of small quantities. So there will be a first parent value, then it is uh, multiplied Okay, so for example, if E is equal to h nu, or you can say some E1 is equal to h nu, then E2 is equal to 2 h nu. Okay, E3 is equal to 3 h nu. The multiples of the values, small quantity, you know, that is h nu is mentioned for the quanta of energy. So normally it is mentioned as photons, and up to En, then it is mentioned as n h nu, where n can take the value of n is equal to 0, 1, 2, 3 up to n. Okay, so 0, then you can mention here E naught also. So E naught is equal to 0 into h nu, so that is also 0. Okay, right. So this is how the values will move. So these are the assumptions made by um, Max Planck, and Max Planck is called as father of quantum physics. Father of quantum physics. And he proposed his own hypothesis and obtained some law which is called as Planck's law of radiation. So that he will derive in, later. So in addition to this, some other scientists have derived the, so in connection to this Max Planck law, that is Planck's law. So Wien's displacement law is there, and one more is Rayleigh-Jean's law. Okay, so first let us see Wien's displacement law. So what is Wien's displacement law? So this law states that the product of the wavelengths corresponding to the maximum energy of radiation and the absolute temperature of the back body is a constant. Okay, so lambda m into T, so that is equal to a constant. So the product of the wavelength corresponding to a maximum energy. Okay, so maximum energy emitted by the black body, so that has a wavelength. So that is lambda m, um, and the absolute temperature of the black body. Absolute temperature means the temperature. Absolute means it is mentioned in terms of Kelvin. So when the product is taken, that is a constant. So this is as per Wien's displacement law. And one more law is there. There is Rayleigh-Jean's law. Rayleigh-Jean's law. So let me tell you that the this law states that the energy distribution of black body is directly proportional to the fourth power of, directly proportional to the absolute temperature and inversely proportional to the fourth power of its wavelength. Okay, so that is given by the energy distribution of black body. So that is directly proportional to T and inversely proportional to fourth power of its wavelength. Okay, so it is like this. E lambda is directly proportional to the temperature and inversely proportional to the fourth power of its lambda. So the proportionality can be removed by E lambda is equal to 8 pi k T by lambda power 4. So this 8 pi k is the proportionality constant. 8 pi k is the proportionality constant. So these are the law. And Planck's law, we can derive it separately. So with this, we can complete this. So this is about the introduction of quantum physics. So thank you.